Welcome back. The aim of this session now is to discuss the second moments of the gradients. And as we discussed during the lecture last week, we developed both the stochastic gradient descent method. We looked at the plane gradient descent. And then we had also an update, which follows what's called the gradient descent with momentum, which we could equally well implement with the stochastic gradient descent. Now, in all the examples which we studied last week, we kept the learning rate, which is the more tricky parameter, which then replaces the second derivative in Newton's method when we are searching for the roots of the gradient. And it simply replaces the second derivative, which is a matrix called the Hessian matrix, which we have to invert for every iteration. It replaces that one with just a constant. Now, in stochastic gradient descent, whether we use momentum or not, or plane gradient descent, we normally would like to specify a schedule for tuning the learning rate as a function of time, or better, as a function of the number of iterative steps. So in the context of Newton's method, this presents a number of dilemmas. The learning rate is limited by the steepest descent direction, which can change depending on the current position in the landscape. And to circumvent that problem, ideally, the algorithm would keep track of a curvature and take large steps in shallow flat directions and small steps in steep, narrow directions. Now, the second order methods, which we are going to discuss pretty soon now, they accomplish this by calculating or approximating the Hessian and normalizing the learning rate by the curvature. Now, this becomes computationally more expensive, and especially for extremely large models. So ideally, we would like to be able to adaptively change the step size to match the landscape without paying the steep computational price of calculating or approximating Hessians. This is essentially the rationale for the second moments of the gradient part, which we are going to discuss now. And the methods which we are going to look at closer are methods called ADAgrad, root mean square propagation, and ADAM, which is the one which normally is the method of choice when we deal with these adaptive methods. So choosing a fixed learning rate is normally hard to get right, as you have probably seen, and which you will also see when you're dealing with the exercises and the projects. So if it is too large, the updates can quickly overshoot the minimum, and you will have oscillations or even divergence, as we saw in the examples last week when we made the learning rate too large. And too large means that it's actually larger than 2 divided by the maximum eigenvalue of the Hessian matrix, if you can calculate the Hessian matrix. If it's too small, on the other hand, the convergence can be very slow, and you will need many iterations to reach the ideal minimum. So in practice, what you end up is actually to use a trial and error or schedules where you have a decaying 8 over time. So when I say time here, it is actually the number of iterations which we are implementing. And you can think of every iteration as representing a kind of pseudo time step. And for a function with steep directions and flat directions, a single global eta may actually be inappropriate. So steep coordinates require a smaller step to avoid oscillations. So one way to avoid the oscillations, which we discussed last week, was actually to implement the momentum, which smears out the steep oscillations by keeping track of the values of the parameters we're updating from a previous iteration. So instead of having only the previous iteration, we take the iteration before that one as well. Now, if we have flat shallow coordinates, we could use a larger step to speed up progress. And this issue is actually pronounced in high-dimensional problems with sparse or varying scale features. So we need a method to adjust this step size per feature. And this is where we have this basic motivation for the adaptive step sizes, where we try to keep some information about the gradients. And these methods represent, in a certain way, a way to approximate the Hessian matrix without having to calculate the Hessian matrix. So instead of a global fixed eta, and last week we also discussed some simpler methods, like a exponential decay of the learning rate. So you start with a value like 10 to the minus 1, and then as you step through, you make it smaller and smaller. You can have a linear approximation, or you can just keep a constant one. So the parameters, the hope then is that the parameters that have large accumulated gradient magnitude should get smaller steps. And this is especially useful if you have very sparse features. That means that rarely active features accumulate little gradient, so the learning rate remains comparatively high, ensuring that they're not neglected. And also if you have frequently active features which accumulate large gradient sums, and their learning rates automatically decreases. So this is also another delicate point where these adaptive methods try to circumvent the problems which we have, especially for the case where you have sparse features. Now, the methods we will focus on ADAgrad, root mean square propagation and ADAM, but there are many, many other ones. So let's take a look at ADAgrad first, and the programs which follow in the Jupyter Notebook are programs which you can adapt to your own projects and exercises and use as much as you want. So the ADAgrad algorithm, and this is taken from the textbook by Goodfellow et al., we would typically start with a global learning rate, which eta, and then we have some initial parameters which can be set to random values, and then we have a small constant which is included in order to avoid the eventual divisions by 0. And then we have what we call a gradient accumulation variable. And you will see quickly what that means. So this is the case when you do stochastic gradient descent, but you can implement it equally well to the standard gradient descent. So in this specific case, you would sample a mini batch examples from the training set. You select randomly your starting point, and then you have corresponding targets. So this is now your training set, and within that training set, you compute the gradients as before. So this is the individual cost functions, and we are selecting only a set of points. So if you're doing stochastic gradient descent, if you do the plane gradient descent, which we also discussed last week and the week before, you will have to include the whole gradient. And then you accumulate the square gradient, and this is a so-called multiplication element by element. And the symbol which you see here stands for what is called a ADAM multiplication. So it means that we multiply element by element. So it's an element by element multiplication. Now we update this parameter, and then we compute the update of the gradients by dividing with this parameter. So in a certain sense, this is mimicking somehow the Hessian matrix, and then we multiply with the gradient here. So this is division and square root applied element-wise. And this symbol, as I said, represents what's called a Hadamard multiplication. And then we apply the update by simply adding this. So previously we had the gradient times the learning rate. This is our original learning rate, which is now diminished by the value of the gradient squared and the square root of that. And then we add this delta parameter in order to avoid eventual divisions by 0 in case R is equal to 0. So this is essentially the algorithm for ADAgrad, and we will see examples of codes below here. So the ADAgrad algorithm maintains a running sum of squared gradients for each parameter. And then we let the gradient, as you see here, to be the gradient at a step t, or a subgradient for non-differentiable cases. We initialize this R0, and then at each iteration t, we update the accumulation by simply adding the element-wise multiplicated gradients here. And by doing that, for each parameter, we can then view what is going to be our pseudo-Hadamard Hessian matrix as a diagonal matrix of past squared gradients, and initially H0 is 0. And then we would have the update rule, as we saw in the compact algorithm, which is taken, if you go back a little bit, this is taken from the textbook by Goodfellow et al. So the parameters or the variables which you see here are then expressed by this variable in the equations here, which is this h variable, which is a diagonal matrix with the different entries. And in the coordinates, this means that each parameter j has an individual step size, which is now given by the 1 over the square root of the accumulated gradients. And we add this parameter epsilon in order to avoid eventual divisions by 0. So this is essentially the ADAgrad algorithm. And if we now scroll down a little bit, we can then, below here, you will find examples of implementations. But the nice thing with ADAgrad is it automatically tunes the step size for each parameters. And each parameters, the parameters become more volatile or large gradients, you get smaller steps. And those with small or infrequent gradients, you get relatively larger steps. There is no manual schedule which is needed. And this accumulation RT keeps increasing or stays the same if the gradient is 0. So the step sizes with eta divided by the square root of these accumulated gradients, they are non-increasing. And this has a similar effect to a learning rate schedule, but individualized per coordinate or parameter. So when I say coordinate here, it actually means per parameter. There is a benefit if you have sparse data. For every sparse features, this accumulated gradient grows slowly so that a feature's parameters retains a higher learning rate for longer, allowing it to make significant updates when it does get a gradient signal. And convergence, if you have a convex optimization problem, actually ADAgrad can be shown to achieve a sublinear convergence rate comparable to the best fixed learning rate tuned for the problem. So ADAgrad is extremely useful if you know that you are dealing with a convex optimization problem. So it effectively reduces the need to tune eta by hand. Now, because this RT accumulates without bound, ADAgrad's learning rates can become extremely small over long training, and that potentially can slow progress. So the other method, which is widely used, is root mean square propagation. And then finally, we will also discuss ADAM. And what is pretty common when you run machine learning codes is to view your runnings as a numerical experiment. And you would, in one case, try out ADAgrad. In the next case, you could try root mean square propagation. And finally, you could also try to include ADAM. And typically what you would end up doing is to explore all three possibilities. And then you would pick the one which gives the best results. So root mean square propagation is actually a method which tries to tackle ADAgrad's diminishing learning rate issue. And it uses a decay average of squared gradients instead of a cumulative sum. So in this case, we have a new parameter which is typically tuned. So this parameter rho is typically set to 0.9 or even 0.99. And the recipe here is simply to update theta by calculating this update, which looks very much like the one we had with momentum. And it actually introduces a kind of momentum aspect, which you have seen before. And the typical update in this case is to calculate this quantity. And then we update the parameters by taking again the learning rate, the original one we started with, and dividing by the square root of this quantity here. And then multiply with the gradients. So that means that recent gradients have more weight. So this parameter VT adapts to the current landscapes, and it avoids ADAgrad's infinite memory problem, having learning rates that means that learning rates that does not continuously decay to 0. So it was actually proposed by Jeff Hinton, one of the founding fathers of artificial intelligence and many of the machine learning algorithms. Actually got the Nobel Prize in Physics in 2024. And this is an unpublished algorithm. And the algorithm is pretty straightforward here. So we would have, again, a global learning rate, and then a decay rate rho. We would initialize the parameters. We have, again, this small constant 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, and it's used to stabilize division by small numbers. We start accumulating R, and in our case, we calculate the gradients. If we are doing a stochastic gradient descent, we select a mini batch randomly with the starting values, and then the corresponding target values. We compute the gradient as before. So the calculation of the gradient is as essential as before. And then we accumulate the squared gradient. So we have, again, the Hadamard multiplication here, but then we have this so-called momentum parameter, which we encountered also when we discussed the gradient descent with momentum. And then we compute the update. And again, the update is done by a element-wise multiplication. And the final update is here. So again, this is also a pretty straightforward and simple algorithm. Now, the question is, why combine momentum and root mean square propagation? So the ADAM optimizer goes a step further. So the motivation for ADAM is to use adaptive momentum estimation, and it wants to combine the benefits of momentum and root mean square propagation. So you get a faster convergence by smoothing gradients. You have adaptive rates like in root mean square propagation, and per dimension learning rate scaling for stability. ADAM uses both, so it maintains moving averages of both first moment gradients and second moment, which are the squared gradients. And additionally, it includes a mechanism to correct the bias in these moving averages. And this can actually be crucial in early iterations. So it's a very robust, and it's often the preferred methods for optimizing the learning rate. And it achieves faster convergence with less tuning and often outperforms, like say, a stochastic gradient descent with momentum in practice. So the ADAM optimizer, if we now scroll down a little bit here, so it maintains two moving averages at each time for each parameter. So the first moment is what we call a momentum term, and you recognize this one as what we have seen before, and so this beta 1 becomes a constant. And then we have the second moment, which now has the element-wise multiplication, and this is now given by, so it's actually two moment updates. So this looks very much like what we had in this step here, looks very much like the one we had in root mean square propagation. And the one you see here is the standard momentum term. So it's a mix of the momentum gradient descent, where we keep track of the information from a previous step. And then we have the second moment, which affects our pseudo-Hessian calculation, where we now have the element-wise multiplication of the gradients. And you see now that the root mean square propagation term here it contains a new parameter. So this is the root mean square propagation, which you saw from the previous algorithm. And then we have the momentum term here, which is the one we discussed last week in connection with both gradient descent and stochastic gradient descent. And the typical values which people have fiddled around with and found to be rather optimal is a beta 1, which is given by 0.9, and a beta 2, which is 0.999. Now, if we now scroll down a little bit here, we can then look at the algorithms. And in this particular case, we would now start with a given step size. So you can, what I would rather suggest is to start with a step size given by an array of step sizes. So you could start with 10 to the minus 4, 10, move to 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, and then use ADAM or any of the other methods with a grid of step sizes. And then you have these exponential parameters, and we would keep the parameters which are suggested by in a paper by Kingma. And we would initialize the initial parameters. We have the same small constant, which is used for numerical stabilization. We initialize the first and second moment variables, which here in the algorithm, which is taken from Goodfellow et al., is called S and R. And then we compute the gradients as before. We have a parameter T, which counts the number of iterations. We update a bias first moment, which is now simply our plane momentum. And then we have the root mean square propagation term, which you see here, which now contains the element-wise multiplication of the gradients. And it contains also this previous parameter. We correct the bias in first moment, and note that this is raised to the power of t, the number of iterations. And this is also raised to the power of t. And then we compute the update with this parameter s here, which contains both the first momentum, where we have tuned the learning rate, and then we have the second one where we in a way are trying to include information about the calculation of our gradient squared, which in a way is meant to mimic in the Hessian calculation. And everything is done by element-wise multiplications. So this is our final algorithm. And if we now look at the different algorithms, we can then make comparisons and see which one gives the best result. And then we would typically end up presenting the results with the algorithm which performs best. Now, the practical tips when we are running the calculations is always to randomize the data when making mini batches. So it's always important to randomly shuffle the data when forming mini batches. Otherwise, the gradient descent method can fit spurious correlations resulting from the order in which the data is presented. So you should always transform your inputs. This is something which we have been discussing in the first weeks and also during the lab sessions. So it's pretty common to actually standardize the data by subtracting the mean and normalizing the variance of input variables, or dividing by the standard deviation. That is pretty common. You may also want, if your data have a big scatter, to scale them down to some x min and x max values. Monitor the out of sample performance. You should always try to monitor the performance of your model on a validation set. That's a small portion of the training data set that is held out of the training process, and that can serve as a proxy for the test set. So if the validation error starts increasing, then the model is beginning to overfit. This is something which we will also discuss in greater detail when we come to the bias variance trade-off discussions. And you should terminate, if that is the case, you should terminate the learning process. And this early stopping significantly improved performance in many settings. Adaptive optimization methods don't always have good generalizations. And it's not given that they will actually give a better result. And this remains to be discussed by numerical experiments. Now, one of the things we are going to do here in order to simplify things is actually to sneak in automatic differentiation in the codes. You don't need to do that in case you're dealing with just a plain ordinary or mean squared error as your cost function, because then the gradient is pretty easy to calculate. But I'm going to show here what is coming later when we are going to write our own code for neural network, is the introduction of automatic differentiation without having gone through the mathematics. So this is a way which gives us much more flexibility in case we have functions which are more complex than those which we are dealing with. And the library ADAgrad is now replaced by JAX, but here we are going to use ADAgrad, and you will see that we are importing ADAgrad in the gradients by simply putting in the statement from ADAgrad import grad, and then we are going to import ADAgrad numpy as NP here. So here I define the cost function, which you recognize as the standard mean squared error. And in this particular case, we are actually using ADAgrad to calculate the gradients for ordinary least squares. And the data set is a pretty simple one with some added noise. We have our own plane inversion, which you have encountered many times. We are using the eigenvalues of the Hessian to find the best optimal learning rate. So in a way, this is nothing but just a repeat of what you have seen before. And then here we perform the iterations without having a proper stopping criterion, which is one of the tasks of the which was one of the tasks of the exercises last week. And we make a plot here. So we are just using now the automatic differentiation, and you see now that the own inversion and the gradient descent here give exactly the same result as expected. Now, we can include the momentum, as we also discussed last week. So the first codes which you see now are essentially a repetition from what we discussed during the lectures last week. So we define the cost function, and in this specific case, when we are dealing with the gradient descent, we are actually, again, using ADAgrad. So the only thing we need now, since we have only one parameter, one variable, theta, we are now setting up the gradient cost of the cost function. So we define the cost function here. This is the standard mean squared error. And then we calculate simply the gradient here. And then we perform the calculation of the gradients in our gradient descent approach. We update the parameters theta, and then we just keep going. And this is the calculation of the same method, but using momentum. As you can see in the code here, we have now updated the new change with this momentum change. So we have this delta momentum, which we now just fix to 0.3. And this becomes a parameter we need to tune. So in this code example, we have first a plane gradient descent, where we have used the Hessian matrix and diagonalized that one in order to find the largest eigenvalue. And that has given us a value for eta, which you see here. So instead of the eta value should be smaller than 2 divided by the max eigenvalue. And when we now do the calculations with momentum gradient descent, so this is just plain gradient descent, there is no adaptive learning rate. It's just starting with a fixed learning rate. And then we do a momentum update. And as we discussed last time, we see now that the result with a known gradient descent with and without momentum obviously favors the momentum gradient descent, which gives a faster convergence, as we discussed last time. And then we can repeat the same exercise just to remind ourselves about what we did last week. And in this particular case, we now do include stochastic gradient descent. It's the same code. Essentially, we have the cost function here. We calculate the eigenvalues. We have the gradient. So this is the plane gradient descent. And then what we do next is actually to set up our stochastic gradient descent, where we have a learning rate, which is now being updated by this function here, so that the learning rate in this particular case shrinks as a function of number of iterations. And in our case, then we fix these parameters, T0 and T1, to just some values. So these become parameters, which we have to fix. And the same is with the number of epochs and with the number of data points in each batch. So this is the size of a given mini batch. And that gives us a number of mini batches, which we're going to sample over. So we run over the epochs. You can think of now calculating an expectation value of the gradient. We place ourselves randomly by picking a random index. This gives us our design matrix. We have our target values, which then correspond to the same values in the as the input values. And then we calculate the gradient, but now you have to remember that we have to divide by the number of points in the mini batch. And then we run over the mini batches and the number of epochs. And every time we update the learning rate, the learning rate, and then the parameters theta. And in this particular case, since we are doing a stochastic gradient descent, you will also see that the values from the stochastic gradient descent for this specifically small case are not as accurate. And you can see that we have a 3.699, 3.181. And then you see that this is the value which we get from matrix inversion, which presumably are supposed to be the best possible values. So you can, the codes which you will find in the lecture notes from week 37, they contain several examples. And in this example here, we have also included the momentum. And you will see that we are doing the stochastic gradient descent with momentum. And there is this new variable, which you call new change. So we have eta times the gradients plus this delta momentum times change. And we initialize typically change to be 0. We fix this delta momentum to be 0.3. So remember again that this becomes a parameter. So theta then is simply just the new change variable. And then we put the change to the new change. And then we keep iterating here. Keep again in mind that there is no stopping criterion here. And in principle, in both the standard gradient descent, which you see here, there should have been a stopping criterion. But this is something which we have left for one of the exercises. So normally with momentum, there is a faster convergence. But still, you see now that when you do a stochastic gradient descent, this is less accurate. But it being compensated when you move to multi-dimensional problems. So this is a simple one-dimensional problem. Or rather, it's not one-dimensional because we have a given number of parameters theta, but the problem is now pretty simple. And when we come to neural networks, we normally would have hundreds of thousands of parameters. And then this is the domain where typically these methods perform much better. So clearly, if we were to use Newton's method, since this is a case where we can calculate the Hessian matrix, what you would find then, if you just use the Hessian matrix, which we have here, and for ordinary least squares, you can pre-calculate that one. And in this specific case, it's being pre-calculated, and then you can use it in the calculation of the update of the parameters theta. So in this specific case, again, I'm using now ADAgrad to calculate the gradients, but you could actually have a function where you return the gradient. So here I've actually just defined the gradient, which is pretty simple, but you could have defined a function yourself which calculates the gradient. And this is essentially what you will be doing in the first project when you're writing your own gradient descent code. So in this specific case, we are simply multiplying, instead of multiplying with the learning rate, we are multiplying with the inverse of the Hessian. This is obviously much more time consuming, but you will see now that the results after just one iteration, you're basically spot on. And you see now that the gradients here are essentially 0 numerically. And this is our own inversion, and this is what you get from our own Newton code, where we have used the Hessian matrix. So clearly, if you can calculate the Hessian, and in particular, if the Hessian is independent of the unknown parameters theta, you could actually run this calculation. This is a calculation which you could run if you also don't have too many parameters. So in this particular case, we are actually setting up a polynomial of degree 2, as you can see here. So we have 1s here, we are keeping the intercept. We have x to the power of 1 and x squared. And our data set is a simple function. And this is a function which we will also look at in the examples below here. So this is clearly an example where we can use the Hessian matrix, and we don't have that big dimensionality because our design matrix in this particular case, since we have a polynomial of degree 2, keeping the intercept is nothing but a matrix of dimensionality 3 times 3. So this is normally a pretty small case when it comes to the computational cost. Now, the next examples here are us including ADAgrad, root mean square propagation, and ADAM as methods to update the learning rate. So again, I'm redefining the cost function. I have a very simple second order polynomial, which is our data set. And I use 1,000 data points. This gives me my own matrix inversion. So this should in principle be the numerically exact result. I set up the training gradient. I have my AutoGrad function here. I am setting up a stochastic gradient descent. And now I'm using the ADAgrad algorithm. So I define a new learning rate. I define the number of epochs, the number of batches. Remember again that these become parameters you would have to play around a little bit with. Normally, when you use methods with a hyperparameter like reach and lasso, the parameters which the results are most sensitive to are actually the learning rate and the hyperparameter. So many practitioners would often fine-tune these two parameters and find the optimal mean squared error, just to give an example, or R2 score, or other types of score which is relevant for that specific case. And then you would start tuning these other parameters with a fixed learning rate and a fixed hyperparameter lambda. Now, in this particular case, we include now ADAgrad, and we have a learning rate. We have this parameter delta, which we discussed earlier to avoid possible divisions by 0. So we have the value of the gradients, which we have squared. So we accumulate these values, as you can see here. So this is the gradient iterated. We are doing a random positioning. We find the random starting point, and then we initialize the array, which we're going to use to calculate the gradients. And then we have the corresponding target values. We calculate the gradients. We iterate, so we have gradients times gradients. So this is just simply the way we would do the Hadamard multiplication. So this is not the same as us setting up this one. That would be the inner product. Now we're just doing an element-wise multiplication. So this is the gradient squared. We have the gradients times the original learning rate, the one we started with. And then we have the diminishing parameter here, where we have the square root of the gradient squared. And then we update our values. So if we run this code, what you will see now is that we are getting pretty close to the exact result. We note an almost perfect agreement with the results from matrix inversion. Now here we could easily have added a momentum update. There's nothing which hinders us from that. But what you would typically do then is actually to do a root mean square propagation. So this is the implementation, our own implementation of the root mean square propagation using stochastic gradient descent. You can replace that one with plain gradient descent if you prefer, but we would normally advise to use a stochastic gradient descent because that would be the method of choice when we are moving on to deep learning methods. So the cost functions is the same as before, boring mean squared error. We're just going to stay with that one. So this means that we're just doing ordinary least squares here. There is no ridge, no lasso regression, or anything more complicated. The same function as before. We leave out the random noise. You could add that one if you want to. We do our own matrix inversion for comparison. And then we have the training gradient given by AutoGrad. We define the parameters for stochastic gradient descent as before. We have a random guess for the parameters. We are assuming that we are going to fit this function, as you can see here, with, again, a second order polynomial, just as before. We scroll down here, we have the eta values, which is our starting learning rate. And then we have this raw parameter, which we discussed. We have this parameter delta in order to avoid possible divisions by 0. And now we accumulate the iterated gradient. This is the stochastic gradient descent part. We loop over epochs. We loop over the number of batches which we have. We place ourselves randomly, m times random round inter, so that finds a random number in this range of variables. We find the indices for where we begin and end for the matrix X. We find the corresponding targets again, and then we calculate the gradient. But now we have an accumulated gradient where we have the scaling with raw with the new and the previous value. So we have raw times the new value plus 1 minus raw times the gradient squared here. And then we take the diagonal only inverting, and then we have the gradients here. So this is again the matrix, in this case is a vector-vector multiplication, and it's a Hadamard multiplication. So it's an element-wise multiplication. So the only difference between this one and ADAgrad is that now we have a momentum update. And if we run the code here, what we end up with is a result which is as good as we found with ADAgrad. So we can clearly update the learning rate. We can have a better learning rate. So we could have a learning rate which perhaps is 0.1. Let's try that one. And then you would see now that the values are a little bit worse for the first one, but pretty okay here. So it's seemingly that learning rate which we had previously was actually much better. So if we rerun it with that one, you see that we're getting closer to the exact value. Finally, our last implementation is ADAM, which combines the best of ADAgrad and the best of root mean square propagation. So again, it's the same example, nothing new here, same cost function. We compare with a second order polynomial, which now, since we don't have any noise, should give us the exact parameters 2, 3, and 4. This is just the exact inversion where we use the analytical formula. We have a training of the gradient. This is the gradient which we get from the ADAgrad functionality. We set up the number of epochs. We again set the parameters to the optimal values which have been fine-tuned. So if you want to read more, take a look at the original paper by Kingma and Ba. And this is linked in this reference here. We have this parameter again, which we also have in ADAgrad and root mean square propagation. And we start with a number of iterations. We loop over the number of epochs. We loop over the number of batches, find the random starting values for the design matrix and the corresponding targets. We calculate the gradients as always. Then we have the first moment from the equations which we discussed earlier, the second moment, and then we have the first moment, the first term octet, which now has this theta value to the power of the number of iterations, and same with this theta 2 to the power of iterations. And then we update the variables following the formula which we discussed earlier, and then we have the theta update. And this is essentially the material which is needed to implement ADAgrad, root mean square propagation, and the ADAM method. And if we run this code here, we see that we get a pretty good result again. Now, to summarize, if you want to look at the different methods, the ADAgrad uses a per coordinate. So per coordinate is actually the parameters which we are looking at, the parameters we are updating. And ADAM, if you look at it, you can think of ADAgrad as an update without any momentums. It tends to slow down too much due to the cumulative history. And ADAgrad is extremely useful when we are dealing with purely convex functions. This may not be the case when we have a complicated deep learning methods with a neural network or convolution neural network. Root mean square propagation uses moving averages of squared gradients, like ADAMS, but to maintain an adaptive learning rates, but it does not include a momentum or bias correction. And then ADAMLY effectively actually includes root mean square propagation plus momentum plus this bias correction. And the momentum provides acceleration and smoother convergence, and the adaptive scaling moderates the step size per dimension. And the bias correction, which is absent in ADAgrad and root mean square propagation, that ensures robust estimates early on. So in practice, what we often see is that ADAM often yields faster convergence and better tuning stability than root mean square propagation or ADAgrad alone. But you may encounter scientific articles where people actually say that in our specific implementation, it seems that root mean square propagation did the best job, or even ADAgrad did the best job. If you have a well-known convex optimization problem, what normally happens then is that ADAgrad is normally pretty sufficient. You can actually also do ADAgrad with momentum, which is getting pretty close to root mean square propagation. So this summarizes our discussions of these different adaptive methods. And during the different lab sessions, we will keep discussing the implementations of these methods, their pros and cons, etc., etc.